Welcome back, everyone, to another college algebra lecture. Today, we are going to be starting on Chapter 3. Chapter 3 is primarily concerned with polynomial functions and rational functions, and we're going to kick it off with polynomials. Now, just be prepared, this lecture is going to be kind of long, but this section covers a lot of material. After seeing a couple of examples, if you feel like you got it, please feel free to skip ahead. But I did put several examples of everything, just in case you have questions. All right, now to start with, we're going to talk about what polynomial functions look like. A polynomial function is just a collection of terms. Poly means multiple, so that's going to be multiple terms. And these terms are going to be made up of a combination of a number and x's raised to a power. Now, the terms are separated by either addition or subtraction signs. And what's going to be special about these to make them polynomials is that for the x's, their exponents have to be non-negative integers. So right here, the exponent for each one has to be non-negative integer. Now, if non-negative integer doesn't work well in your brain, just think about it like this. Exponents will never be, since we're going to do integers, I cannot have a fraction in here. And non-negative means that it will never be a negative. And that's the two main things we look for whenever we're talking about polynomials. Now, when you write, got a little ahead of myself. I'll come back to it later. When you write out a polynomial, we always want to try to write it out in standard form. Now, standard form is very easy to spot and very easy to write it in. All you have to do is just make sure that you write it in descending order of degree. Now, that's just a fancy way of saying biggest to smallest exponent. That's it. So you want to write this from biggest to smallest exponent. Okay, now once you have it written in the proper way, it's pretty easy to pick out some certain things. First, all the numbers that are located in front of your x's, those are called coefficients, and those are going to be real numbers for us. They can be any number I want. Fractions, negatives, radicals, anything I want can be out in front of an x because it's coefficient. When you write it in standard form, your biggest exponent is going to be first. The number written in front of it is called your leading coefficient. And the very first one is called your leading term. So the leading term has an x. The leading coefficient is just the number that's with it. So that one is just a number. Okay, the last one, if it does not have an x on it, is called your constant term. Now, it's called constant because as I put x's in here, they change these because I have x times a number. But this one, since it never has an x multiplied by it, it will stay the same no matter what x I put in there. So it's the constant. And the one that is arguably the most important is the degree. The degree is your largest exponent in the polynomial. So whatever the biggest exponent is in there, that is your degree. And your degree is super important. It gives you a lot of information that we're going to use going forward. Okay, so that's everything about the function when it's written out as an equation. Only thing I want to mention about the graphs of a polynomial is that the graph of every single polynomial will be smooth and unbroken. Now, smooth and unbroken, smooth just means that there won't be any sharp corners, and unbroken means there won't be any jumps. So kind of how when we did piecewise functions, how there was a jump between them, we're never going to see that here. Alrighty, so at this point, first thing I want to do is I just want to go through and identify whether something is a polynomial or is not. And if it isn't, let's figure out why. So looking at this first one, I see that I have x1 at 2, x1 at 1, nothing. This one's a polynomial. And since it's a polynomial, I can write out what the leading coefficient and degree is. So my leading coefficient is 3, and my degree is 2. So again, your degree is your biggest exponent, and the leading coefficient is the number that's out in front of that x. So once you find one, you find the other. Okay, looking at b, I see that in my exponent, I have a fraction 2/3. Well, since that is a fraction, I know for sure that this is not a polynomial. Done. Okay, looking at the next one, I see that this one has a negative. So if there is a negative in my exponent, that is automatically not a polynomial. And that's all there is to it. Okay, take a look at D. This one, I see that there's a fraction and I see that there's a radical, but that's perfectly fine because those are coefficients. They're out in front of the x. Looking at my x's and the exponents, I have 1, 3, 5, and none. Everything's fine. This one is a polynomial. It's just not written the way that we normally would write it. So taking a moment to write this one in standard form, the first one is my biggest exponent. So this term's going to go first. So that's going to give me negative 7/5 x to the 5th. Then my next one would be plus square root of 2 x to the 3rd. Then I would have plus 8x and then minus 1. That one is now written in standard form, 5, 3, 1, 9. So now that it's written the correct way, I can say my leading coefficient is negative 7/5, and my degree is 5. Nothing else to do. Now, take a look at the last two. This one definitely is not written the way that I would imagine a polynomial would be. But remember, if I have something on the outside of parentheses, I can distribute. So let's rewrite this. Distributing that 3x, I see that I have 6x to the 3rd minus 3x. That is a polynomial. So if you ever get it to where it's written like this with parentheses, that just means it's factored. If you distribute it back, you can find out what your degree and leading coefficient are. So right now, my leading coefficient is a 6, and my degree is 3. All right, now for the last one. This one is a bit fun, and I like it quite a lot. Looking at it, you might guess that it's not a polynomial, just because you don't see any x's. Well, there is an exponent property that you've been taught in the past that says anything to the 0 power, or I guess I should say anything except 0 to the 0 power, is equal to 1. That means I can rewrite this one right here as negative 3x to the 0 power. Because if I do x to the 0 power, that x goes away and I'm left with the negative 3. Well, 0, that's not negative, that's not a fraction. This is a polynomial. So every constant function is a polynomial. My leading coefficient right here is negative 3, and my degree is 0. That's it. So spotting a polynomial, pretty quick and easy. Make sure that there are no fractions or negatives in the exponent. And your degree is the biggest exponent. The leading coefficient is the number found in front of the x with the biggest exponent. All right, now let's take a look at some graphs. I want to figure out whether these graphs could be polynomials or not. Looking at this first one, I see that there's a break. So this one is broken. Since it's broken, that means it's guaranteed not to be a polynomial. Done. And I'm going to skip over to this one real quick. Looking right here, I see this comes to a sharp corner. So since it has a sharp corner, I know that this one is not a polynomial. Done. Problem solved. These last two right here, they are smooth and unbroken, no sharp points, no jumps. That means that they are both possibly polynomials. Now, I use the word possibly because there are other functions out there that are smooth and unbroken, but are not polynomials. So I just want to draw attention that these could possibly be polynomials, but it's not guaranteed. But for the purposes of our class, I'll just go ahead and just put poly for both. But you've already seen that I can give you a piecewise that's smooth and unbroken. That's not a polynomial. All right, so hopefully you feel pretty comfortable with some of the terminology we're going to use: coefficients, degree, leading coefficient. Now we can take that and expand upon it. So going over to the next page, we're going to start talking about zeros. And luckily, we already have a good background on this because we talked about zeros when we did quadratics. We know that a zero is where our graph crosses the x-axis, or you can think about it as that's where our function equals 0. So there are two ways to think about this. You can think about it graphically, and you can think about it algebraically. So zeros, which are also referred to as roots, those are where we cross or touch the x-axis. Those are referred to as the x-intercepts. And that's also where our function is set equal to 0. So the x-intercept part, the crossing or touching, that is the graphical way of thinking about it, or the definition graphically. And whenever the function set equal to 0, that is the algebraic way of thinking about it. So two different ways to think about this. All right, now I keep mentioning cross or touch. I wanted you to look at this graphic up here. Anytime I say that we cross the x-axis, it would look like this, these three right here. You are on the bottom, and then you go to the top. And then you can be on the top, and then go to the bottom. You have to cross physically through the x-axis. If I say touch, that means that you are under, hit the x-axis, and then you are still under. You hit a ceiling, bounce back. Or you could be above, hit the bottom, and you bounce back up. Both sides of the 0 are on the same part of the x, or above or below the x-axis. So cross, you go through it, touch, you hit it, and turn back around. That's going to be very important to us, especially on the next page, that you understand cross and touch. Alrighty. Now, I gave some extra information over here for zeros, but these are the two that I mainly want you to think about. Algebraic, that's where our function equals 0. Graphically, that's where we have x-intercepts. And now we can start figuring out some zeros. Looking right here, if I want to figure out the zeros of this polynomial, first off, I want you to realize that is a polynomial. It's just factored. I can go through and distribute. This would wind up being a quadratic. It'd be 5x squared plus some. Well, if I want to find the zeros, I know how to do this. I would just set the whole thing equal to 0 and solve. So setting this equal to 0, I would see that I get x equals -1 and x equals 2. Got it. And if I were to look at the graph, I would see that I went through the x-axis here and back through the x-axis right there. Now looking at this next one. This one might not be as clear, so I will take a point and point something out to you. When we do this, we do the zero product property, and I split it into 3 pieces. So I would have 1/2 x equals 0, x minus 2 equals 0, and x minus 7 equals 0. Right here, just multiply both sides by 2, and I get x equals 0. Move the 2, I get x equals 2. Move the 7, I get x equals 7. I don't have to worry about this square right here because I know I would wind up taking the square root of both sides to cancel it out. So I'm just kind of taking advantage that I think you can figure that one out. So here I had 3 zeros. The only reason I took the time to break this one down is because a lot of students sometimes get tripped up on this x out front. If you ever get x out here by itself that's outside of a parentheses with no plus or minus with it, it's always going to be 0, because when I split it up, whatever number's in front, we just divide it away, and x will be 0. Only whenever you have x plus or minus something will you get x actually equal to a number. So x on the outside by itself, guaranteed to be 0. All right, now for the next two, we can do this algebraically, or you can do it graphically. So I'll go ahead and factor because we know how to do this algebraically. And I'm going to skip writing down the ABC method because I think I've beat that to death by this point. But if you still want to do it, keep doing it. I have no problem with you showing a little extra work. Nothing wrong with that. So factors of -3 that can add up to be 2, I see that I can use x minus 1 and x plus 3. Got it. Now solving each one of those, I see that I get x equals 1 and -3. And alternatively, if you wanted, you could have done this graphically. Graphically, I could have done x squared plus 2x minus 3. I see that I have x-intercepts at -3 and 1. So you can do it algebraically, which I would prefer because it keeps skills fresh in your mind, or you can do it graphically. Graphically won't always work though, especially in I think 2 lectures when we get to stuff you can't see. All right, now one more to go ahead and beat this dead horse. I can set that equal to 0. Do my ABC method, I see factors of 30 that it can add together to be this would be -5 and -6. So that means x equals 5 and x equals 6. Got it. Cool. So I know I have x-intercepts here, 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 and here. But there's something special, and I want to bring your attention back up here to B. Up top, whenever I was talking about cross and touch, something special is going on. So cross, I told you we go through. Touch, they wind up being on the same side. Let's look at this graph right here and see what it looks like. So putting this one in, I have 1/2 x times x minus 2 squared times x minus 1, or x minus 7. All right, so looking at this, I'll zoom in so you can see it a little bit clearer. I see that I cross through the x-axis at x equals 0, because there's the top part, there's the bottom part. I cross through when x is 0. I touch right here when x is 2, because I'm below the x-axis on each side. So I touch at 2, and then I cross through at 7. So the question that I really want you to think about at this point is, what determines whether I cross through or I touch? That's the main question. Well, it can't be that it's a positive number because 2 and 7 are both positive, and one touches, one goes through. So it doesn't look like it's what the 0 is itself, but I want you to check out the difference. Look at the exponents for each of these factors. Not the x themselves, but the factors. Right here, this exponent is 1, that exponent's 2, and that exponent is 1. For these two exponents that are 1, an odd number, my graph crossed through. But right here, when my exponent was 2, 2 is an even number, and I touched and bounced. That's a pretty good idea of what's about to happen. So what we're going to do is we're going to talk about what determines whether we cross through or touch. And we were looking at the exponents. That's actually exactly what you're going to do every time. Look at the exponents. Therefore, on to the next page. If you look at the exponent of a factor, the power of a factor, that is called the multiplicity. So looking right here, this is a kind of wonky definition. Looking at this, I would say x equals r, because I would move the r over. Well, since the exponent is m, I would say that x equals r has multiplicity m. Now, it's not as pretty to talk about whenever you only have letters. So let's actually look at some numbers. I typed this one up for you before we got down to the main examples. I give you this polynomial f of x equals x plus 1 to the second power times x minus 2 to the third power. Well, I can tell by looking at this, I have a 0 at x equals negative 1 and a 0 at 2. Well, the 0 at x equals negative 1, that came from this factor right here, x plus 1 to the second power. Well, since the factor has exponent 2, that means that x equals 1 has multiplicity 2. And right here, my 0 at 2, that factor has exponent 3. That means x equals 2 has multiplicity 3. So all you do to figure out the multiplicity is look at the exponent. Now, if this still hasn't sunk in yet, which I don't blame you, it's kind of a confusing topic, I want you to think about it in a different perspective. And this is probably the part that will probably make the most sense. If I were to write this out, x plus 1 to the second power times x minus 2 to the third power, I can expand this. I'm not going to distribute all that foolishness. But anything I know is squared means that it's times itself. X plus 1, x plus 1. Third power means I'm going to have 3 of them. X minus 2, x minus 2, x minus 2. So looking at this, I see that x equals negative 1 2 times. So this counts as a 0 twice. So this has multiplicity 2. The multiplicity is the number of times that it counts as a 0. And personally, that's my favorite definition of this. The multiplicity is the number of times that it counts as a 0. Here, since I had 2 of them, it counted twice. Here, I have 3, so x equals 2 counts 3 times. It has multiplicity 3. That's what I want you to think about. Figure out how many times it's a 0. The way you figure out the number of times it's a 0 is look at the exponent, because that's how many times it'll show up. That is your multiplicity. And now bringing this back to the graph that we saw on the previous page, if your multiplicity is even, that means that your graph will touch and turn around. That's it. So if I say it touches and turns around, that means it's going to look like this. It'll be above and then go back. Or it would look like this. It would be below, touch, and then come back. That's what it means to touch. If your multiplicity is odd, that means you cross through the x-axis. If you cross through the x-axis, that means that you are literally going through it. You go from being on top to being below. Or you can go from being below to being above. Like that. So cross, you physically go through it, touch, you hit, and you turn back around. The way you figure that out, look at the multiplicity. Even multiplicity touch, odd multiplicity cross. All right, so at this point, all I want us to do is figure out what the zeros are, and then what the multiplicity of that 0 is, and whether it crosses or touches. So looking at this first one right here, I see that my 0 is going to be x equals 5. And since the exponent's 2, it counts twice. So this one has multiplicity 2. I usually like to abbreviate down to just an m. Now for the next one, that is going to be x equals negative 2. Since my exponent's 3, it counts 3 times. My multiplicity is 3. Now as far as crossing and touching, since this one is an even multiplicity, that means I will touch right there. Since this one is odd, that means I will cross right there. I don't know what the rest of my graph looks like, but I know right here, it's going to touch and turn back around, and I know right here it's going to go through, guaranteed. Alrighty, now for the next one, I have 4 zeros. So my first 0 is -5. That has multiplicity 4 because the exponent's 4. I know that means I count 4 times. For the next one, I have -1. This one, if there's no exponent up there, I know it's a 1, just like on the last one. So that means I have multiplicity 1. Generally, you never write the multiplicity, but just to drive the point home, I'm going to put it there. So the next one, I would have 2 with multiplicity 3. And the last one, I have 4 with multiplicity 1. Now, as far as crossing and touching, this one's even, so that means I touch. This one's odd, so I cross. Both of these are odd also, so those cross as well. Done. All right. Now, if you're already solid on this and you want to move on, stay for one more example, because I got one more thing I want to remind you about. Right here, finding my zeros. You need to remember, if you ever get x on the outside by itself, no plus or minus behind it in parentheses, you know that x is going to be 0. If I set that equal to 0, I would get rid of the negative, I'd get rid of the 3, I'd still get x equals 0. That one has multiplicity 3. Now for the next one, I have x equals 3 with multiplicity 2. And my last one, I have x equals -2 with multiplicity 1. Done. And as far as what these look like, I know for these two odd ones, I'm going to cross. And for the even one, I touch. All right. Now, if you're already good after that, go ahead. But I do got one more example if you want to see it. Here, I see 4 factors. So I know my first one's going to be 0 with multiplicity 2. My next one, x equals -1 with multiplicity 7. My next one is x equals -7 with multiplicity 1. And my last one, x equals 9 with multiplicity 2. So right here, I know this one will touch, and this one will touch as well because they are both even. And both of these will cross because they are both odd. Got it. So we now have a very good understanding on what a graph is going to look like in terms of its x, or as far as its zeros, and how to figure out whether it's going to cross or touch. So that gives us a good idea of what a graph is going to look like without even using our calculator. And based on some extra stuff we're going to do, you'll be able to figure out a bit more. All right, now moving on. This next one, I want to build up to a property to help better your understanding of what's going on. So we're going to do a little exploration together before I just give you a rule and say follow it, because I want you to know what's happening. Now, also be very well aware that I don't care about the accuracy on these graphs. So when I graph all 4 of these, it's just going to be an estimate and not perfection. So I graph these ahead of time, so I'm not going to put the calculator up here. This one, if I graph it, it looks similar to this. Just follows the same shape. Are my points accurate? No, I'm very well aware. Don't get upset. My degree for this one is 2, because that's my biggest exponent. My leading coefficient is 2 also. For this next graph, I know this one looks like this. It goes up, comes back down, goes up, and then it goes back down again. And my degree for this one is 4. My leading coefficient is -4. Got it. Now for the next two, this one looks a little something like this. I go up, I come down, and then I go back up. Got it? My degree is 3. My leading coefficient is 2. And for the last one, this one, I start up here, I come down, I go up, kind of curves a little bit, and then it goes back down. And my degree is 5. My leading coefficient is -5. All right, so we're going to use these graphs plus the leading coefficient and degree to figure out some information. So for this first question I want to answer, what difference did we notice between the functions with an even degree and functions with odd degrees? And I want to give you a little tip on what to look for right here. When we're asking this question, I want you to look at the arrows. So looking at the arrows for this one, both of these are even. Well, I see both of these arrows are pointing up and both of these arrows are pointing down. So for even, the arrows are going the same way. Both of these have odd. Well, when this arrow is going down, that arrow is going up, and this arrow is going up, this one's going down. They switched, but the key thing is one was going down, one was going up. So it looks like if our degree is even, my arrows point the same way, and if my degree is odd, my arrows point opposite ways. Turns out that will always be true. No matter what polynomial we're working with, that is a true statement. So writing out our observation, even equals same direction for the arrows, and odd equals opposite. Let me say that. Opposite directions for the arrows. So even is same, odd is opposite. Got it. All right, now for the next one. Here, what differences did you notice between functions with a positive leading coefficient and functions with a negative leading coefficient? And I want to give you a tip again on what I want you to look at. So right here, I want you to look at the right arrow. So just the right arrow. All right, well, we're talking about positive and negative leading coefficients. I see both of these have positive leading coefficients, and the right arrow is going up. Both of these have negative leading coefficients, and the right arrow is going down. Turns out that will always be what happens. If your leading coefficient is positive, your right arrow will go up. If your leading coefficient is negative, your right arrow will go down. Now, I do want to take a second and give you a little bit of background as to why that is true. The reason that is going to be true for us is because over here on the right side, the right arrow, all of our x values are positive. Well, no matter what exponent you raise a positive to, it's going to come out positive. So I'll have a positive number here for x times a positive number for the leading coefficient. A positive is positive. It goes up to the positive world. On the other hand, if my x's are positive, I'm still going to have a positive. But if I multiply that positive number by a negative leading coefficient, a negative times a positive is a negative. It goes down to the negative world. That's what's going on right here. Now, do you have to memorize why? No, but I think it sometimes helps you remember if you understand the reasoning behind it. That, and I like to talk about it. So right here, if our leading coefficient is positive, that's going to mean right arrow goes up. If our leading coefficient is negative, that means your right arrow goes down. And that's something that's going to help us out later when we figure out what our graph looks like. Because now I know by looking at the function whether it's going up on a side, whether the arrows are going the same direction, and I also know if I cross through the x-axis, it'll touch or bounce. So I can kind of draw an outline of what a graph's going to look like without knowing all the details, which is very powerful. All right. So on this next page, we're going to formalize this a little bit. What we were just talking about with the arrows is the end behavior of the graph. So anytime that you see end behavior, what I want you to think about is arrows. So right there. So the end behavior, those are the arrows at the end. That's it. So end behavior is arrows at the end. Now, end behavior theorem, you can go through and read it. This is something that's really useful in calculus. So if you know this college algebra class is just a starting point for you and you're going higher up, this is pretty important. If you know you're stopping around here, just buckle up. It's not bad. All right. Now I want to take a moment and talk about how we describe the end behavior. Because so far I just said, oh, I'm going up on the left. There's a proper math way to describe this. Now, looking at this graph right here, I see I have two arrows. That means I have to describe the end behavior for both arrows. Each arrow has its own behavior. These are both going the same way. These arrows are going different. So you always have to describe both. Now, to help us out, I'm going to go ahead and put my infinities around this. That's going to help a lot when it comes to looking at what's going on. And I know it might seem a little silly, but it truly does help out when it comes to describing these. So give me a second to put these on here. And if you don't understand this stuff super well, do the infinities. It'll help you out. All right. Now, when we describe these, I want to say this arrow right here is going up on the left because I have two arrows, left side and right side. Well, this one's going up. Well, if I talk about up means up and down. That's y. So if I want to talk about going up, that means the y is going to positive infinity. So right here, I would say y, you put a little arrow. The arrow means goes to positive infinity. All that means to me is arrow goes up. Up is y. Now to take care of the fact that it's the left arrow, well, left and right is the x-axis. So I'm going to say x goes to, here I'm on the left, that means negative infinity. That's it. So the mathematical way of describing this is I would say y goes to positive infinity as x goes to negative infinity. All this means is go up on the left. That's it. Now for the next one, this arrow goes up. Always start with y. Since up, that means y is positive. And I'm on the right side. So right side means x is positive. So this says y goes to positive infinity as x goes to positive infinity. And if that's not kind of clicking well, think about it as coordinates. Right here, this coordinate is positive y, negative x. Over here, positive y, positive x. That's all you got to do. Now, as far as this one goes, I want to keep that degree and leading coefficient stuff fresh on our brain. So right here, I see that my arrows go the same direction. So since my arrows go the same way, that means my degree is even. And my right arrow goes up. Since the right arrow goes up, that means my leading coefficient is positive. And conversely, if I gave you a polynomial with an even degree and positive leading coefficient, you would know exactly which way the arrows go now. All right, looking at the next one, describing this arrow, we always start with y. I see my y is going down. that means negative infinity. And since I'm on the left side, that means x is negative also, which makes sense because this quadrant is negative, negative. All right, now for the next one, I see my y value is going up, so that's positive infinity, and the x value is on the right, so that's positive also. This quadrant is positive, positive. Now, as far as my degree and leading coefficient goes, I see that my degree, since they go opposite directions, my degree is odd. My leading coefficient, since my right side goes up, my leading coefficient is positive. Got it? All right, now for the next two. I'm going to do a little bit of a switch right here. It's more common in math, instead of saying y, to say f of x. So I want you to remember this little math fact that you've been told over and over again. So recall, y equals f of x. I've said that before in this class, and you've heard it before in other classes. So all that means to us right now is instead of writing y, I'm just going to switch to saying f of x. That is the standard way of doing this. And if you do take calculus in the future, that's what you would say. So doing this arrow points down, so my y value, which is f of x now, goes to negative infinity. And since I'm on the left side, that means x goes to negative infinity also. And this kind of makes a little bit more sense. As my x values go negative, my function value, when I plug them in, goes negative also. Now doing this one over here, f of x goes to, well, since I'm pointing down, I'm going negative, and I'm on the right side, I go positive. All done. Now figuring our degree and leading coefficient. For my degree, since they go the same direction, I know it's going to be even. And for the leading coefficient, since the right side goes down, this one is negative. Got it. Now for the last one. This arrow points up. That means the y value, f of x, is going to positive infinity. And since I'm on the left side, x goes to negative infinity. And for this last one, my y value is going down, so f of x goes to negative. And I'm on the right side, so x goes positive. Done. Now for the degree, they're pointing opposite directions, so my degree is odd. And since my right arrow is going down, my leading coefficient is negative. All done. And for a polynomial, these are the only four combinations that you're going to get. It's either both go up, both go down, one side up, one side down, and then those two switch. So in behavior, shouldn't be anything too terrible. All right, now one reason this is going to be really useful for us, we know how to describe it when you have a graph, but combining what we know about the leading coefficient and the degree, we can describe the end behavior without even seeing the graph of the polynomial at all, which is useful in, say, calculus, again, if you want to figure out where the graph is going without actually having to graph it, because graphing some things is a beast. So for these examples right here, I am going to use a little bit of a graph, but it's just a sketch, just a little baby one. So to start with, I'm going to put a set of axes down right here, and then I'll put my infinities around it. Infinity, negative infinity, positive, and negative. Got it. All right, looking at this, my degree, that's the biggest exponent, is 2. My leading coefficient, that's the number in front, is 3. Got it. Now, I know that my degree is even, my leading coefficient is positive. So when it comes to doing a problem like this, always start with your leading coefficient because you know that talks about the right arrow. So my right arrow, these positive x values, positive times a positive goes positive. Got it. So I know my right arrow. Now using what I know about the degree, since my degree is even, I know the arrows go the same direction. Do I know what goes on all in the middle? Absolutely not. Well, actually I do, since this one's a parabola. But I don't know what's going on in the middle. I don't know the vertex. I don't know any of that foolishness, but I know where my arrows are going. So I can write my end behavior right here. My end behavior, I know f of x is going up, so positive on the left side, negative, and f of x is going up, positive, on the right side, positive. Now, at this point, I do want to take a little bitty break and point out something that I kind of hope you've already noticed yourself. When we're talking about polynomials, they're smooth and unbroken. They go forever, both ways. Both ways, both sides, left, right. There will always be a left side and always a right side. Looking back up top, you always had a negative x and a positive x. Guaranteed to happen for polynomials. So when it comes to doing a problem like this, you can go ahead and say negative infinity and positive infinity. It's never going to change. The left side's always negative, the right side's always positive, and there's guaranteed to be a left and a right. Kind of hope that you saw that earlier, but just in case you didn't, I wanted to point it out to you. All right, looking at the next one, I'll do the same thing, and I'll go ahead and draw this for all of them. So excuse me while I concentrate and be quiet. Enjoy it while you can. Okay, so I hope you enjoyed the silence while you had it. Looking at this one right here, I see that my degree is 4. So already I know that's even, my arrows are going the same way, but I don't know if they're both going up or both going down. Well, our leading coefficient is -5. So right here, leading coefficient talks about the right side. Positive times a negative goes negative. Think about it like that. Positive times a negative is negative. And since my degree is even, they go the same way. They both go down. So writing my answer, I know f of x goes to, as x goes to, well, left side is negative infinity. This one goes down, so that's negative infinity. Now for the next one, I have f of x goes to, as x goes to. On the right side, that's positive. It's still going down. That's negative. All done. For C, I see that my degree is 3. My leading coefficient is -2. So my right arrow, positive times a negative, is negative. And since my degree is odd, that means I go opposite directions. One up, one down. So right here, I see that f of x goes to positive infinity as x goes to negative infinity, up on the left. And then I go down on the right, so down is negative, right is positive. Finished. Now for the last one. I see right here, my degree is 5, my leading coefficient is 4. So leading coefficient on the right side, positive times a positive goes positive. Odd degree, opposite sides. So now I have f of x goes to negative infinity, goes down as x goes negative. So down on the left, and then I go up on the right. So f of x goes to positive infinity as x goes to positive infinity. All done. So hopefully you're not sick of end behavior yet. And if you were thinking about calculus, don't let this scare you. It's actually pretty fun. All right, so in behavior combined with what we know about zeros, we can get a good general shape of what our graph is going to look like, which is really useful for us in the future, especially when it comes to doing inequality stuff coming forward or in the future. All right, now moving on. This next page, we're going to talk about turning points. So a turning point for our graph is where we change from increasing to decreasing. Think about it as turning directions. If you're on a roller coaster and you're going up, you are increasing. But at the hill, you start to decrease. You start flying down and screaming. You turned, you changed direction. So if you ever change from increasing to decreasing, that's going to look like a little hill. That's the same as a local max. So a local maximum, that was the top of a hill, like that. And if you ever change from decreasing to increasing, that is the bottom of a dip. Looks like that. So a turning point is where I turn and change direction. And I have to go from increasing to decreasing or decreasing to increasing. Having this little slight bend doesn't matter if it's still increasing. All right, now on this one, we're going to do another little exploration. And this one, again, I graphed them ahead of time and they're not going to be super accurate. So if I don't go through the right points, chill out. It's fine. All right, this one I know looks kind of like this. Got it. The next one, this one goes up, comes back down, and then goes back up. And this one goes up, comes down, and then goes back. Got it. Now for these three down here, this one looks like this, kind of like a big old parabola. This one goes down, kind of bends a little bit, and then goes back up. And for the last one, this one comes down, goes up, goes down, comes back. Got it. So what I want us to do is look at the function itself, figure out the degree, and then the number of turning points. So looking at this first one, I see my degree is 3. As far as the number of turning points, if I trace this, I am increasing the entire time. I might kind of bend a little, but I'm still increasing. So I have 0 turning points. A little bend doesn't count as a turning point. For the next one, this one's degree 3 also. I'm going up, I have a hill, I come down, have a dip, I go back up. I change direction twice. Look for a hill and a valley. Now for the next one, degree 3 again. I went up, went back down, and then back up. I changed direction 2 times. Got it. Now for these 3 down here, they all have degree 4. Got it. This one has 1 turning point. I change direction once. This one, it might bend a little, but I'm still going down. I only change direction once. Now for the last one, I have a dip, a hill, and another dip. I have 3. Done. So an observation that we can make. One observation I notice is that if I have an odd degree, my turning points were even. That's kind of a good observation. If I have even degree, I have odd turning points. That's a good observation. But that's not what our book is looking for. The biggest, most general observation that doesn't have to split it into even and odd categories is that my turning points are always less than the degrees. And that's what we're about to explore next. So right here, what we need to notice is the number of turning points is less than the degree. That's the big overall general observation that we need to see. All right, so going on to the next page, exploring that a little bit further. Bam, a theorem. Now, this theorem is stated out or written out using proper math. You can go through and read it, but if you are not fluent in mathematics, I can break it down for you. This basically just says that your maximum number of turning points possible is always one less than the degree. That's it. So right here, max possible turning points is one less than the degree. That's it. So if you have degree 4, the maximum turning points possible would be 3. If you have degree 10, the max possible would be 9. It's always one less than your degree. So these problems are probably the ones that you hope I give you for the rest of your life, but I won't, because they're super easy. So looking at the first one, my degree is 5. That means my maximum turning points is 1 less, 4. Now, does that mean I'm guaranteed to have 4? No. I could have 2. I could have something else. I could have 0. But that's the maximum possible. And I do have a little example coming up that's going to be a little off script, but just want to do this next one. So this next one is degree 6. That means the maximum possible would be 5. Done. Now at this point, I'm kind of hoping someone out there in virtual land is thinking, why? Why is it possible for it to be 1 less? Why can't I actually equal my degree? And at that point, I want to show you this right here. If I were to give you this, I want to try to draw degree 4 and 4 turning points. I want to try and do this. All right, so I'm going to start up here. I'll go down. That's 1 turning point, 2 turning points, 3 turning points, 4 turning points. I cannot turn anymore. That's what I'm left with. Well, I got an issue right here. I have 4 turning points, but degree 4 means they have to have the same arrow direction. These arrows are pointing opposite directions. So the only way I could have had my arrows point the same way is if I didn't turn right here and left it at 3 turning points, or if I turn back this direction and come back up, which means I would have had 5 turning points. Now, there's something else going on mathematically that we have not gotten to yet that's going to keep me from turning back around, because that means I'm going to have too many zeros. Spoiler alert, that's something important. So I would have had to have stopped right here. That couldn't happen. So it is not possible to have the same degree in number of turning points. All right, now moving on to these next ones. These are factored. So figuring out what your degree is takes a little more effort. Now, would this one be terrible? Nah, we can distribute that, create the quadratic. But what about this one? This one's going to be a pain in the butt, because I would have to write out x plus 4 5 times, distribute, then do this 3 times, that twice. It would be a complete and total nightmare. I would rather quit math than do that. But there is a way around this. I'm going to give you a tip, And this tip works almost all the time. There's only a few exceptions. And for everything I give you, it will work. So right here, to find the degree of, to find the degree if the polynomial is factored into linear terms, those are the parentheses, and by linear, that's the ax plus b. There's no quadratics. So linear terms, the parentheses, all you have to do is add the exponents of the factors. Now, the only factors that are going to have the exponents are ones with x's. So I'll put that right here, with x's. That's all you have to do. Now, the part that I was saying a moment ago about this will only work for certain situations, the certain situations is this part, the linear terms. If I had like a square inside the parentheses, it would be a different situation. But I'm only going to give you linear terms, so that's all you have to do. So we're just going to add the exponents. So bringing that back up here with what we know, this term right here doesn't have an x, so I'm not worried about it. That has exponent 1. That has exponent 1. So that means my degree is 1 plus 1, which is 2. That makes sense, because if I were to go through and distribute and get the expanded form, this would be a quadratic, x squared. So my maximum number of turning points is 1. All right, now for the next one, this has exponent 1 over here. Since this term has an x, I count it. 3 plus 2 plus 1 gives me 6. So my max turning points would be 5. Done. Now for the next one, this has an x, so I count it. There's a 1 on top, so that's 1 plus 4 plus 2 equals 7, which means 6 is my maximum number of turning points. Now for the last problem, I have negative 7 on the outside. That does not have an x on it, so I do not care about it. All I care about are the ones with x's. So I have 5 plus 3 plus 2 gives me 10. That means my maximum number of turning points is 9. And we're done with turning points. Now, again, that does not guarantee that you are going to get that many turning points, but it gives you a maximum number possible, which can be helpful. All right, now for the last little bit. And these are my favorite problems. This is going to bring back in the multiplicity, big time, big time. So what we're going to do is I want to write a polynomial, f of x equals something that fits the graph. So this is something pretty important. And this is actually something that happens a lot in the real world. Say you go out and collect a lot of data and then you plot it, you might see that it follows a particular shape. Well, that shape, you want to make a function for it. That way you can predict stuff in the future. This happens a lot. Like a lot of engineers, physicists, it's super important to be able to do this. But a key factor on the problem that I just gave is this right here. I want to write smallest degree possible. That's going to be a huge thing for us. The reason why is, looking at this one, I see that both my arrows go up forever. So both point up. That means my degree for this one is even. But that means I could have degree 2. I could have degree 4. I could have degree 6, going on forever. It's not super helpful to write it with the biggest degree possible because there is no biggest degree possible. But it is a little bit more useful and concise to write it with the smallest. Now, I'll come back to that in just a second. So when you're attacking a problem like this, what you need to do is start by identifying your zeros. Looking right here, I see I have a 0 at x equals -3. So I'll write that out, x equals -3. And to help us out, this is going to be important, I see that I cross through the x-axis. So I'm going to go ahead and write cross. My next 0 happens right here at x equals -1. Here I see I'm on the same side, so this one is a touch. Now for my last 0, I see that it happens right here when x is equal to 2. This one, I cross. This is super important to us because over here, I know I can now write out x equals -3. And the cross part, that's going to tell me my multiplicity. Because the multiplicity we see is very important. That's going to tell me the exponent on this factor. So right here, if I want to write this as a factor, this would be parentheses x plus 3. Because remember, it's the opposite sign. I had to move it over. But I need to know what exponent to put on there. Well, since I cross, that means my exponent up here is odd. That could be 1, 3, 5, 7, 9, go on forever. This is where the smallest comes back into play. So if I cross, I want the smallest number possible for me to cross at. So cross is going to equal multiplicity 1. That's because 1 is my smallest possible odd number that I can use. All right, now as far as touch goes, this touch means even multiplicity. The smallest even number that I can use that's actually useful is going to be multiplicity 2. Yes, I know 0's an even number, but 0 is not going to help me out much because it kills everything on it. All right, so bringing that back over here. This crosses, that means this has multiplicity 1. So my exponent's 1. For this one right here, x equals -1. That is going to have multiplicity 2 because I touch. So writing it as a factor, that's going to be x plus 1 to the second power. And for my last one, I have x equals 2. Since I crossed, that means multiplicity 1. So as a factor, that's x minus 2 with exponent 1. Got it. These are my factors when I write this out. So writing out my polynomial, I have f of x equals, right here, very key detail on it. Take a look on the previous page. Looking back here, I see that I could have a number out in front of my factors. That's important because that number, if you remember our transformations, is the stretching or shrinking. That makes sure I hit all the points necessary. So I got to leave a blank space or put a constant in there to keep track of that number. So what we generally do is just put an A. That A keeps track of my stretching and shrinking, and that's something we're going to need. All right, so now I can fill in my factors, x plus 3 to the first power. I don't need the 1. Right here, x plus 1 to the second power. And then right here, x minus 2 to the first power. I don't need the 1. Well, that's the hard part, really, in my opinion. But I can't leave it like this. As tempting as it is, I can't say that that's my polynomial because I got that a in there. That a isn't very useful. I got to know what that number is. Well, the way we figure this out is look for a point on our graph that does not, or that's not one of our zeros. So just look for any random point that you can name for sure. This one I see right here. That point is the point 0, -3. The reason we look for this is because, remember, every ordered pair, that's x, comma, f of x. So now I know that I can fill in 3 for f of x, and if I put, negative 3 for f of x, and if I put negative 3 here, that means 0 has to go in the x spot, because those two numbers go together. So filling this in, I know I have a, I'm going to plug 0 in for x, 0 plus 3, 0 plus 1 squared, 0 minus 2, and anywhere I put 0 for x, the corresponding f of x value is negative 3. So where there's 1, the other has to go. Well, now the only variable in there that I don't know is a. All of this right here, I can figure out. That's going to be 3, that's going to be 1 to the first power, which is 1, times negative 2. That gives me negative 6. So I have negative 3 equals negative 6a. Divide both sides by the negative 6, and I get 1/2 equals a. Now all I got to do is take that back up here to the original. So my final answer, f of x equals 1/2. And make sure you put the x's back in there. Don't leave zeros. So I have x plus 3, x plus 1 squared, x minus 2. All done. And if you were to type this into your graphing calculator or whatever you use for graphing, you would see that it matches this graph perfectly. And you're all done. All right, so I'm going to do one more. And if you're good after this next one, you can go ahead and check out. Or if you want to see 2 more, I have 2 more on the next page. But at least stay for this next one because I got something special on it. Nothing crazy, just a little special. So this one, we're going to attack the same way. Always start by figuring out your zeros. I see that I cross right here. So I have x equals 0, and I cross through. You see I'm above and I'm below. So that one is a cross. Then I also go right there where x equals 1. And that one is a touch because they're both below the x-axis. In this one, it was nice and friendly and gave me my extra point. So I know that's x, comma, f of x. Got it. So now, writing out the stuff I know I have x equals 0. Since this one's a cross, that means multiplicity 1. Then I have x equals 1 with multiplicity 2 because I touch. Perfect. Now, writing out my factors, I don't have anything to move over. Remember, if it's ever x equals 0, that means it's just x by itself. So x to the first power. Then over here, move the 1 over. That gives me parentheses x minus 1 with x1 at 2 because I have multiplicity 2. Got it. Now I can write out my general form. F of x equals a. Now I'll put my x to the first power. And then x minus 1 to the second power. Got it. Now I can use my extra point. So I know my f of x value is negative 4. I don't know a. My x value is 2. So I have 2. Then 2 minus 1 squared. Well, that's going to be negative 4 equals, this is 2 minus 1, that's 1, 1 squared is 1, that is 2a. Divide the both sides by 2, and I get negative 2 equals a. Now I just take that back up here, and that gives me f of x equals negative 2x times x minus 1 squared. And we're done with that one. So the only thing special on this one is to make sure that if you ever have x equals 0, it's just going to be x by itself. All right, so if you're good after that, you're welcome to go. But if you still want to see a couple more, I got 2 more examples, and then I'll be done with the video. All right, so looking at these, I'll go through them pretty quick because we already know how to attack these. So for this first one, I'm going to start with my zeros. I see that I touch right there, so x equals 2. That's a touch. And then right here, I have x equals 7. That one is a cross. Perfect. Now I'm going to go ahead and pick out my extra point. I see a dot right here. That one is the point 0, negative 14. That's x. That's f of x. All right, listing out what I know I have x equals 2. That one is a touch, so means multiplicity 2. And then right here, I have x equals 7. That one's a cross, so multiplicity 1. Writing my factors, this is x minus 2 to the second power. This one is x minus 7 to the first power. For the general form, we have f of x equals a x minus 2 squared x minus 1 to the first, so I leave the 1 off. Now for my extra points, negative 14, a, my x value is 0, so I have 0 minus 2 squared, and then 0 minus 7. Got it. So at this point, I see that I have 0 minus 2, which is 2, or negative 2. Negative 2 squared is 4. 4 times negative 7 is negative 28. Divide both sides, and we get 1/2 for a. So I can take that back up top to my original and fill the a in. So f of x equals 1/2 x minus 2 squared x minus 7. And we are done with that one. Hopefully you're picking up that these follow the same exact pattern every time, and they're pretty good to work with. All right, now for the last one. Doing all of our same stuff, I see right here, this one's a 0 because my y value is 0. So I got x equals 0. That one is a touch, so touch right there. This one, the y value is 1, so that's not a 0. That's my x, f of x. And for this last one, this is where x equals 2. That's a touch also. Got it. Now I can knock it out pretty quick. I know x equals 0 with multiplicity 2, and then x equals 2 with multiplicity 2 again. Now writing my factors, this one is just going to be x squared because there's nothing to move over. This one is going to be x minus 2 squared. All right, writing our general form, I have f of x equals a x squared times x minus 2 squared. Now filling in my extra point, I know that's 1 squared, and then 1 minus 2 squared. That's going to be 1. That's negative 1 squared is 1. I'm going to write down an extra step that would probably make some math teachers cringe, but just to do it, this is all 1. That means a equals 1. Bringing that back up here, we get that f of x equals, since it's 1, I don't have to put it. I'll just do x squared times x minus 2 squared. All right, and that brings this lecture to a close. Sorry it was so long, but there is a lot of information to cover. If you have any questions, please feel free to contact me, and I will be more than happy to help you out. Other than that, have a great rest of your day.